So I welcome all the participants who are present here to attend to my presentation. But before I could begin with my presentation, I'd like to give you all my quick and brief introduction. So I'm Ritwik Basu, a mechanical engineer by my undergraduate qualification. After having worked in a few different manufacturing industries, mostly pertaining to metallurgical processes, I then decided to take on a master's in material science and engineering. So after completing master's, I joined the PhD program at the Indian Institute of Technology, Bombay, with the Department of Metallurgical Engineering and Material Science back in 2007. The project I was working then was a funded project under a UCARE initiative. So while a PhD student at IIT Bombay, I was a visiting researcher at the Imperial College London. I started my career once again in industry with Oxford Instruments in their Indian operations as an application specialist and worked for a short stint before moving to Canada for my postdoc research at the University of Saskatchewan. And lately I joined academics after coming back to India. So it's been close to 6 years now in my academic job role, and currently I'm an associate professor at the Bharatiya Skill Development University in Jaipur in India. So ours is a Swiss-funded university geared towards imparting skills-based education to Indian youths, and I head as the principal of my school, that is the School of Metal Construction Skills, dealing with metal fabrication, welding, and other stuffs. So that was all about my introduction in brief. Now, my research is about process design engineering. So what I mean by process design here is essentially we look into the different metallurgical mechanisms that are associated during component fabrication through various engineering processes. So these processes could be one of the engineering processes such as rolling, forging, extrusion, or sheet metal working, or even the most sophisticated novel processes like 3D metal printing or net ship manufacturing. So we essentially look into the microstructure development that takes place during any of these processes or in their combination and try to infer or relate the properties of the material from the microstructure development. So my research is therefore essentially a very narrow specialty under manufacturing engineering, or what I call as process engineering. Now, when we talk about manufacturing engineering from a systems approach, what is important is that a manufacturing facility exists, and that is really a value adder. So as you could see right in this figure, there is a manufacturing facility that is adding value to an input material, which in this case could be a raw material, which otherwise has no value. But once the value is added, the output that we get out of such a facility generates a lot of wealth. Because the output has some value coded in it. Therefore, it is important to plan the facility in a manner so that the value can be added. And if the value can be added in a right manner, then the product can be positioned in a right manner. And that is the reason why a manufacturing facility exists. So if I take a manufacturing system that has a manufacturing facility, then it really comprises at the heart a set of manufacturing processes that is the key to the wealth generation. So on one side, as you could see, there are various input parameters like sales fluctuations, raw material cost and availability, then the business environment, and on the other side, your production rate and quality, your profit and reputation to keep in the business are all important for such a manufacturing system. But nevertheless, such a system will be balanced and will work well if the key to it, which are the manufacturing processes, are well designed and well balanced. Therefore, the processes automatically becomes the bread and butter for such a manufacturing system. Now, traditionally, manufacturing industries have brought metals to the forefront of technology, and since then they have remained there, forming the very foundation of our modern society. So you could not have imagined a life in which the transportation and communication systems, or could be the buildings, infrastructures, roadways, or even your safety and comfort devices are not part of your daily lives. And you see metals everywhere. Of course, today many new material candidates have been seen to complementing metals and alloys, and composites are one such examples. But my fair feeling is that metals will still comprise the widest spectrum of applications, even for more number of years from now. So here are some insights into the various scales of manufacturing industries, from light industry to heavy industry, where the backbone is metal. So some of these industries include chain of processes such as the production of raw metal or steel to make the final products, while some use precast raw material for component manufacturing and fabrication. So all these industries work in the combination of process and production. So some industries may have a very well established process and strives for routine manufacturing, while some industries are constantly looking to upgrade their process. They are looking for new modification in the process and also design. So when it comes to process modification and design in the class of industries I'm referring here to, it is important. One of the factors which is important is, of course, understanding the behavior of the materials and also the underlying metallurgical mechanisms that goes behind the processes when raw materials are subjected to specific treatment for component fabrication. So there's different metallurgical mechanisms, as I was earlier referring to, could also depend on several factors such as the physical and chemical state of the metallic or the alloying elements, then of course the extent of recovery or recrystallization during annealing, or could be even the formation of intermetallic compounds or precipitation of secondary phases during solidification. So all these different mechanical or metallurgical mechanisms are likely to occur during one or the other processes or in their combination, which I discuss shortly, which includes rolling, forging, extrusion, or even welding, heat treatment, and a lot more. So as a mechanical engineer or a manufacturing engineer or maybe a process engineer, it is therefore important to understand the behavior of material when raw materials are subjected to a specific kind of treatment or process. And the way we look at it is that the factors involved in manufacturing, such as the properties of the raw materials, which could be machinability, forgeability, or even weldability, or the factors of the final component during in-service application or in-use applications, could be largely controlled by dictating the microstructures or understanding the microstructural mechanisms that goes behind the processes. So we are essentially looking into this process structure property relationship, and the kind of materials that we mostly talk about are the metals and alloys. Now, microstructural analysis could refer to a wide variety of analysis typically conducted at the level of micro or nano in metallic material system. And there are various techniques and tools which are available these days. So this information could be both qualitative and quantitative. So information such as understanding the arrangement of dislocations and the interaction in corework specimens or in course of core working, or looking into the distribution of precipitates or secondary phases along the grain boundaries, or even understanding the phenomena of recrystallization or recovery during in situ process or during annealing, or even looking into the crystallization pattern during solidification of metallic melt through high-end optical microscopy techniques. So these variety of informations could be inferred through techniques such as transmission electron microscopy or scanning electron microscopy, then electron basket diffraction imaging, or even the high-end optical or metallurgical microscopy. So I must tell you that my research is twofold. One that I already discussed is understanding the different metallurgical mechanisms associated with different engineering processes, and then inferring or relating the properties of the process component from microstructural standpoint. That forms one part, and the other part of my research is, of course, materials characterization or microstructural characterization during through high-end scanning electron microscopy techniques such as electron basketed diffraction or energy dispersive spectroscopy. So, of course, X-ray diffraction is another vertical I work on. So I must tell you that I'm a microscopist and I have handled different versions of scanning electron microscope during my past and present research. So here are some glimpses of my research into microscopy, the various labs I've worked in the past, to give you a fair idea about my skills in microscopy techniques. Now, to give you a better illustration on this process property microstructure relationship in materials, we have this example of this car body part manufacturing. Now, as you could see, these car body parts are made up of sheet metals of steels, which are processed through hot rolling and then cold rolling, where a significant thickness reduction occurs. Now, the obvious question that arises is the same thickness reduction could have been achieved through a much simpler process, such as sheet casting, which would have been more economic and time-saving. Then why do we go for such complex deformation processes? So cold rolling or plastic deformation process, apart from obtaining dimensional changes or shape deformation in material, also introduces certain interesting properties which other processes possibly do not offer. So cold rolling or plastic deformation introduces grain refinement and texturing in the microstructure, and that is seen through a significant change in the mechanical properties or the mechanical behavior of the materials. So the strength is seen to increase by several times, however the ductility drops. Now the problem occurs when you try to give further deformation to these cold roll sheets to obtain these nice contours and profiles, as you could see in this car body part. Difficulties arise because your sheets have been so much strain hardened, as a result of which doing any kind of further deformation in the subsequent processes may lead to cracking or failure in the sheets. So we have to think of alternative mechanisms of softening these cold roll sheets, and we adopt certain techniques such as heat treatment, such as annealing, which includes recovery or recrystallization, that makes the sheet softer so that it becomes easy for the next subsequent deformation processes. So here I have a nice interesting video to show you how these sheets are processed in the industry manufacturing line. So as you could see, the sheets are fed into a complex die mold arrangement, and typically a few thousands of pieces of the sheets are just produced in a few hours. But prior to this deformation, the sheets have been sufficiently annealed for a significant time and temperature so that it becomes soft and easy to deform in the next subsequent processes. So cold rolling, as I was discussing earlier, introduces significant grain refinement and texturing in the microstructure, and that results in high strain heterogeneity in the material. So the strength is seen to increase by several times, however the ductility drops. And interestingly, upon annealing, the grain refined microstructure is retained together with a nice distribution of fine equiax ferritic grains. And the strain that was induced largely during the cold deformation is also relaxed during the annealing stage, thus making the sheets more softer. So the ductility of the material again increases. However, the strength drop is not so significant. So the beauty of heat treatment is therefore to impart the material with the right combination of strength and toughness. And the way we do it is through fine-tuning the microstructures. And that annealing can alter the microstructure significantly could also be understood through this following example. So this is an example taken from one of my earlier research works on nickel titanium shape memory arch wires used for orthodontic applications. So the nice thing about these wires is that at low temperatures, these wires exhibit a phase that is highly deformable. So you can twist it, turn it, give it any shape. While at high temperatures, typically when these wires come in contact with the body, it undergoes a phase transformation, and together with that is a shape change which is associated. So these wires are actually trained to go to a particular shape at high temperatures, and this is what we call as a training in shape memory alloys. So during the clinical use or clinical treatment, these wires are inserted into the oral cavity from a low temperature state, and when these wires experiences a temperature change, it undergoes a phase transformation and a shape change, as I was telling you earlier. And during this shape change, this wires exert small forces on this misaligned teeth to bring it to a more correct position. And this is how the treatment goes. So typically the treatment time takes from 3 months to few years, depending upon the complexity of the misalignment of your teeth. It is therefore important to control the phase transformation temperature window in these materials, and we tried to look into how fine-tuning the microstructures could control the phase transformation characteristics in these materials. So we tried to simulate the processing of these materials through lab scale deformation process called marforming. So this is typically carried out in liquid nitrogen atmosphere. It's a very sophisticated process. So the post-marformed and the post-annealed microstructure brings out significant differences. The same region has been seen under microscope before and after annealing. So what we could see in the post-marformed or the post-deformed microstructure, there's a significant strain heterogeneity that is seen through dense dislocation blocks or walls. That means a higher dislocation density, which could not be indexed for EBSD, and that is the reason why some of these regions appear black. So we tried to further look into these dislocation structures through transmission electron microscopy, and we found that certain grains had this banded structures of dislocations. So these grains which had these dislocation structures were found to have orientations typically denoted by ND parallel to 111 orientation, so these blue colored grains. And interestingly, upon annealing, fine clustered grains of ND parallel to 110 orientation of these green grains were seen to be evolving in these regions of higher dislocation density. So marforming without annealing shows no phase transformation. However, slight annealing could bring back the transformation in process seen through this pair of peaks in the calorimetric plot. So the transformation here I'm referring to is the transformation from the high temperature state to the low temperature and the reversal of phase transformation. So again, marforming without annealing introduces significant strain heterogeneity that is seen through dense dislocation blocks or dense dislocation walls that acts as obstacles for the phase boundaries to transform during the forward and the reverse transformation. The ease of phase transformation actually depends on the extent of annealing, the annealing time and temperature. However, there are other factors too, the mode of deformation, the level of deformation that can also significantly alter the microstructure that in turn can also control the phase transformation characteristics in these materials. So this was work that I carried out during my PhD research, and it was one of the interesting part of my PhD thesis. Now, okay. So the microstructural analysis that I have been discussing so far not just only refers to the processes, but can also be used to evaluate the performance of process component during in-use or in-service application. So this is another work from my previous research on night alloys, the response of microstructure to phase stability or phase transformation during repeated thermal cycling in nickel titanium systems. So we were looking into how spontaneously microstructures respond to irreversibility during phase transformation. So the first slide here explains what irreversibility in microstructure are all about. So the idea was to mark a region, a specific region on the sample and see the same region repeatedly after every thermal cycles. So we have fixed the corner of a grain by the black L shown and have marked a dot at the center of another grain. We then had overlaid across here right on the top of the dot. So what we could see after a few number of thermal cycles, though for our convenience we have shown for the first and the 10th thermal cycles. So after a certain number of thermal cycles, there has been some shrinkage in grains. Some grains have bulged, and that led to a significant displacement of the dot. So basically, this inverted L and the crosshair can be assumed to remain fixed to a reference, and the dot is a movable thing. So there is a clear signature of microstructural irreversibility. So we actually generated a few different microstructures through the Marr forming route, followed by intermediate and final annealing treatments. We then had subjected each of these samples to one thermal cycle. So what we could see is that the microstructures, though different, the textures are not significantly different. But what is more importantly different is the irreversible strain, or what I call as a non-recoverable strain, which is varying from the lowest of 0.06 in sample A to the highest of 0.41 in sample D. So we actually measured the change in the grain size for identical grains before and after thermal cycle, and we did it for some 100 different grains for every different microstructures out of the 6 microstructures, and then took the weighted average. So that is what my delta D average or the irreversible strain is. So the delta D average varied from 0.06 to the highest in sample D, as I was saying, 0.41. So this is some 2 orders of magnitude different. So the question here is, why should sample D exhibit such an aberrant behavior or an aberrant value? So here the sample D is the bad guy. That means it shows the highest of the irreversible strain, and this is not a preferred microstructure. So why? To answer to this question, we had to look into the microstructures very carefully for all the 6 different samples. So what could we see was, although all these microstructures more or less resembled identical, but a careful look into the microstructure showed that all these microstructures had distribution of fine grains. However, the sample D showed the largest clustering of the fine grains. So to answer why should sample D show such an aberrant value lies here. It is largely because of the fine grain clustering. So we have found a parameter K that will define the fine grain clustering as a microstructural quantity, and we defined the K parameter as a ratio of the length of the fine grain boundaries to the total grain boundary length in the microstructure. So as you could see, with increased clustering of fine grains, the effective grain boundary, fine grain boundary length between the fine grains increase, and that increased the value of K. So the plot of delta D versus K shows a nice correlation with sample D exhibiting the highest of the K value. So the first conclusion from this study was that the irreversible strain or the non-recoverable strain, which is indexed with this quantity called delta D, is purely a function of the clustering of fine grains. So we chose the sample D and subjected this to a few more thermal cycles. We did till 50 thermal cycles. So this quantity delta D, or the irreversible strain, as I was stating earlier, is orientation sensitive. And this is brought out in this plot of delta D versus D. So after having done the first thermal cycle, we saw these data points were nearly linear. And we then had fixed an upper and a lower control limit with our best estimate in between, so that all these data points lie between the upper and the lower control limit. And we found that with increased number of thermal cycles, these data points moved upward, and the grains that exhibited the highest delta D were sensitive to these orientations. So the second conclusion from this study was the irreversible strain is, or this quantity delta D, is very much orientation sensitive. So we also found that the increase or decrease in the delta D average did also coincide with similar or identical changes with the average misorientation and the fraction of retained monazite. So this is brought out in this plot where we had superimposed the delta D with the fraction of the retained monazite and the average misorientation estimated from the EBSD microstructure. So we found that ideal orientation relationship exists between the austenite and the retained martensite, and that comes out to be 40 degrees 001 in our case. So any deviation from the ideal orientation relationship or phase boundary relationship of 40 degrees 001 will not allow the martensite to retain or to revert back to austenite during the reverse transformation, and that will eventually lead to higher fraction of martensite during successive thermal cycles. So we found that with increased number of thermal cycles, the average misorientation increased, and that led to a corresponding drop in the number fraction of the 40 degree 001 phase boundaries. So the final conclusion that was made from this study was that the irreversible strain largely depends on the deviation from the exact phase boundary orientation relationship. So any deviation from the ideal orientation relationship will lead to increase in the irreversible strain. So that was from my earlier research work on nickel titanium alloy systems. I must tell you that I have worked on this particular material candidates back during my PhD and postdoc research for almost 6 years. I am familiar with the processing, then analysis of the properties both at the microscopic and macro scale. So a significant time of my research went for analysis of the properties of Shep emery alloys. Back during 2011, this was a project funded through UCARI, and I got an opportunity to work on these materials both at the lab scale as well as the industrial scale. But I must tell you that much of my research interests in recent years have focused on fusion welding and metal fabrication all these years in my academic position, interpreting the problems that normally occur during fusion welding and evaluating the weld metal performance from a microstructural standpoint. Now, the way I work with my students is that I first identify a problem that is of more practical interest to industry, and then see the feasibility of conducting or simulating these processes at a lab scale with my students. Only then I take on a research problem. So I have a few good collaborators from different industries, mostly in the metal fabrication segment, those who help me in designing particular students' research problem for projects, and that is our work with industries. So we have previously worked on dissimilar welding of steels and aluminum alloys, of which steels looks to be quite interesting. Now, dissimilar welding is an emerging area in the welding science and technology, and many applications in aerospace, marine, automotive, or even the power sectors have been largely benefited from dissimilar welding. So this process has importance in applications where combination of properties are desired to be present at different regions or locations within the same part of the component of the structures. So, there are applications that may require, say, a high thermal resistance in one region, while a high corrosion resistance in another part of the same component. There are also applications that may require a high wear resistance or toughness in one region combined with high strength in another location. So dissimilar welding in steels is increasingly becoming common these days, especially in piping and structural welding. So we have examined the dissimilar welded structures of steels, such as stainless steel welded to mild steel. We saw the different microstructures that were generated as a difference in the heat input that also led to significant differences in the strength of the material. So the microstructures were seen to vary from large grain distribution of single phase gamma austenite to fine grain distribution of mixed phases of gamma austenite and delta ferrite. Again, the austenite grain boundary fractions between these samples were notably different. We found that for samples exhibiting a two-phase microstructures, a particular orientation relationship between austenite and delta ferrite exists. However, their relative presence differed between the samples. So the strength of the welded joint was seen to be a clear function of the low-angle grain boundary fraction. So low-angle grain boundaries exhibit a discrete dislocation area inside a grain, while high angle grain boundaries primarily remain at the actual grain boundaries of the material in the microstructure scene. So with increase in the low angle grain boundaries, these dislocation walls are refined and finely spaced, therefore impeding the movement of the other slip dislocations to move across the boundaries, leading to strengthening of the weld joint when stresses are applied. So the decrease in the strength and ductility of sample E, as could be seen here, with increase in the low angle grain boundary fractions, could be related to the lowering of the stored energy. And stored energy is actually the driving force that reduces the mobility of dislocations. And that led to early fracture even at lower stresses for the sample E. So we found that the low angle grain boundary fraction correlates well with the stored energy estimated from the Reed-Shockley's equation measured from the grain boundary misorientation criterion. And we have also seen that with increase in the ferrite content, the impact energy in the samples reduced, especially for the samples that exhibited a two-phase microstructure. So overall, we have shown that a two-phase microstructure is indeed important for imparting a good combination of strength and toughness. So this was a work of mine. So all that I'm going to present here now is my MTech students, because as a faculty, you no more do your own research. It's after all this your students' research. So these are all the results from my students' research project. So this got published in 2018 in Journal of Manufacturing Processes. Now, these differences in the microstructures, as I was discussing, not just only depends on the process variables used, but also largely depends on the also brought about by changing the processes even under identical conditions. So changing the process, for instance, from tungsten inert gas welding to activated tungsten inert gas welding can alter the microstructure significantly, and that can also have a strong influence in the properties of the material. And that is largely because of the differences in the cooling rate that actually plays a vital role in determining the final microstructure of the weldment. So in the case of activated TIG welding or A-TIG welding, an activated flux is applied on the material which are to be welded, and that leads to constriction of the R, leading to increased current density in the anode road, and also this increases the arc forces on the weldment. So when welding stainless steel or any other steel through A-TIG welding, the cooling rates are significantly increased. It is actually that the heat affected zone of the carbon steel side in the case of TIG welding shows a more fine equiax ferritic microstructure, while the heat affected zone of the carbon steel side for A-TIG welded specimen shows a Widmaster ferritic structure that introduces significant grain refinement. So a difference as could be seen between the TIG and the A-TIG welded specimen could be because the heat affected zone underwent a two-phase transformation during cooling. A high temperature transformation from delta ferrite to gamma austenite, and then gamma austenite to alpha ferrite in the second state. Now during welding, when all other material properties are uniform, the cooling rate depends on the amount of molten metal available and also the availability of the heat sink to conduct the heat away from the melt. So in case of TIG welding, the weld pool is much shallow and the arc energy heats up the weld region and the surrounding region to a much higher extent. So therefore, the nuclei of the austenite grains that are formed grows by advancement of the planar interface for a longer duration of time. While in the case of A-TIG welding, the weld pool, as you could see, is much deeper, narrower, and the arc energy does not heat up the surrounding regions to the same extent as in the case of TIG welding, and therefore the has can cool down much faster. So this is partly speculative of why these differences in the microstructures could be observed through TIG and the A-TIG welding. Again, the relatively high strength of the A-TIG welded specimen could be attributed to the higher in-grain misorientation in the microstructure, and also due to the formation of the Widmaster structure that introduces significant grain refinement. Also, the measured hardness profile and the residual stress brings out some interesting observation. Although it is known that the maxima in the hardness corresponds to the minima of the compressive residual stress, but with our samples, we did not see a direct correlation between the hardness and the compressive residual stress. So the residual stress that was measured along the weld surface exhibited a well-like profile, slightly shifted on the stainless steel side. Now, again, why this shift is not clearly understood, but what is speculative is the thermal mismatch strains between the stainless steel side, which had a FCC structure, and the weldment that had a VCC structure could possibly be responsible for the shift in the well-like profile. So this was another work done by my students in collaboration with my Canadian supervisor, which got published in the Transaction of the Indian Institute of Metal back in 2017. Now, another problem that industries faces when welding stainless steel structures is solidification cracking, or what we call as a hot cracking. So it is actually the formation process of shrinkage crack during solidification of weldment or weld metal. So we have examined, done a detailed microstructural analysis to investigate the reasons for solidification cracking in stainless steel weld. We tried to simulate this hot cracks in lab scale samples at different welding speeds. So the morphologies of the cracks were pretty different between the samples, and these differences were also seen in the microstructures of the weld regions around the crack areas. So the EBSD mapping revealed that these cracks were mostly transgranular in nature. So the cracks were seen to propagate mostly through the low Taylor factor grains, so the softer grains that had orientation suitable for slip activation, and the crack propagation was mainly assisted by deformation slip around the plastic zone of the crack tip. So it was also brought out that a higher strain concentration were seen to be associated around the cracks with increasing propensity, and this was verified through the local misorientation distribution that shows significant heterogeneity between these samples. So these local misorientation points, as could be seen in green color, were accumulated more at the subgrain boundaries that were primarily the low angle grain boundaries. So we also found that this crack sensitivity not just only depends on the average misorientation of the microstructure, the weldment microstructure, but also depends on the distribution of the misorientation in the microstructure. That means how your defects or dislocations are distributed in the microstructure. That also decides the crack sensitivity in these materials. So the possible reason, or the primary reason for cracking could arise due to the thermal mismatch strains that develop during solidification of the residual liquid that is trapped between the interdendritic regions. So these cracks are usually seen to accumulate more at the higher welding speeds. However, for our samples, the samples that exhibited a low tendency to cracking possibly constituted a less stable liquid film. So with increase in the welding speed, the tendency towards forming a stable liquid film was more likely, and that increased the strain concentration around the liquid, leading to higher cracking tendency. So this is a work of another MTech student of mine, which is under communication. So I must also tell you that the selection of these processes based on the microstructure criterion is also important for many applications. As in case of the crankshaft production, crankshaft you can produce through two different processes, forging. The preferred process is the forging and casting. However, forged crankshafts are much superior to cast crankshaft used in automotive application. Usually, forged crankshafts are used for high-strength, heavy-duty application, whereas cast microstructures are usually, or cast crankshafts are usually used for lightweight applications where there are chances of less impact or fatigue. But what so brings a difference in the properties between the cast and the forged microstructure is again understood from a microstructural perspective. So as could be seen, forged microstructure exhibits texturing as well as fine distribution of grains that actually leads to grain boundary strengthening and partly anisotropy that makes it superior for many high strength application. Whereas cast microstructures are good for cast crankshafts are good for applications that require a high abrasion resistance or wear resistance. So therefore, choosing between two or more processes when there are various processes available, you have to make a judicious choice from a microstructural standpoint. And crankshaft example is the best example to showcase. So, with that, I'd like to come to a conclusion of this presentation. So, all that you could possibly understand is that the properties of the material becomes an important criterion both during the processing as well as in service application or in use application, and these properties are largely governed or dictated by the microstructural mechanisms that occur during a process or the end microstructure that you attain after processing. So this is a subject which has much potential if you are trying to explore problems, specific problems related to manufacturing. Though mechanical engineers are not very handy with microstructural analysis, but this is not also a very difficult subject to understand, though this largely lies with the scope of metallurgical engineering. But at times, as I was discussing earlier, persons who are involved in manufacturing, they have to really understand the criticalities of the processing as well as applications. And a microstructural standpoint understanding is indeed important. So for students, I have a suggestion. If you're really looking to work on some novel technique pertaining to manufacturing, you can possibly seek my reference or seek my help, guidance. And for industry practitioners also, I would say I'll be happy to take on problems specific to manufacturing processing, or even, as I was telling you earlier, in-service application. This is another area, vertical that I work on. So I'm always available at any time, at any point, and you can reach me through WhatsApp cell, mail me, and also communicate through LinkedIn. So with that, I'd like to conclude my presentation, and I'll quickly show you my school. As I was telling you earlier, I was a Swiss-funded university, and I had as the principal of my school, the School of Metal Construction Skills, that largely deals with metal fabrication, welding, sheet metal production, and all these activities we do it. So we have a large range of welding machines, mostly arc welding machines, all imported. We have laser cutters, plasma cutting machines, then sheet bending machine or press brakes. Then we have very high quality shearing machines, saws, and we also have recently procured a cold forging press and a deep drawing press. So with that, I would like to thank you all for this presentation, for attending this presentation. Once again, have a nice day and a weekend. Thank you very much.